Hey y'all, I'm Gracie and this is Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to calculate the magnetic field of a bar magnet on axis and off axis through a series of measurements with the bar magnet at different distances and a magnetometer app, then coding the magnetic field of a bar magnet using the experimentally determined magnetic moment. The main physics principles are the Biot-Savart law, properties of on-axis and off-axis magnetic fields, and properties of magnetic dipoles. A quick summary of results: mu is calculated to be 6.6134, n is equal to negative 2.9921. The experimental 45-degree axis field is 8.228 times 10 to the negative 5 teslas, and the coded 45-degree axis field is 5.71757 times 10 to the negative 5 teslas. First, we have to set up the experiment. You have to determine where Earth's magnetic north is. This is done by using the magnetometer app and making sure your x direction reads 0. Next, you need to find the magnetometer chip on your phone. That is done by orienting your phone in first this direction, which is perpendicular to the magnet, and you want to maximize the x direction and minimize the y direction. Next, you flip your phone so it's on axis with the magnet, and you minimize the x direction and maximize the y direction. You place tapes in each of these locations, and as you can see, where these two tapes intersect up in this corner is where your magnetometer chip on your phone is. Next is our on-axis magnetic field. This is the data from that. We have the different distances, the magnetic field in the x direction, their averages, and the graph which shows all of this information. More about the on-axis magnetic field. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This allows us to even make any of these calculations. We know from the graph y is equal to nx plus the natural log of k. N is equal to negative 2.9921. This is close to the actual n value for a bar magnet, which is negative 3. N is the power distance is raised to show the magnetic field's dependence on distance, so this value makes sense. K is equal to mu naught over 4 pi times mu. Since we want mu, we have to take e raised to the natural log of k, which allows us to solve for k. Then we manipulate the equation to solve for mu, which is 6.6134. Next, the off-axis magnetic field, which is at a 45-degree angle. You want to calculate d perp, which is this distance over here, and you also have the Earth's y direction magnetic field, the x, the y, and the z. Something about the magnetic field in the y direction is it's initially incorrect. It takes into account the Earth's magnetic field in the y direction as well as the bar magnet's magnetic field in the y direction. Since we only want the bar magnet's y direction, we need to look up the Earth's magnetic field in the y direction based off your location. In my case, it was negative 2.137 times 10 to the negative 9 teslas, and all I had to do was add it to the measured value to get the correct y value. The off-axis magnetic field is based off of this equation. Calculating all of that, the average magnitude of magnetic field off-axis was calculated to be 8.288 times 10 to the negative 5th teslas. The coding. This is the bar magnet. These are the perpendicular arrows. These are the on-axis arrows. And this is the 45-degree arrows as printed down here. This is the perpendicular distance, and this is the magnitude of magnetic field at the 45-degree distance. And that is 5.71757 times 10 to the negative 5th teslas. This is how the magnetic field was calculated. This is the function that I coded. It's based off of this equation down here. Next, we have the perpendicular and on-axis arrows and how those are created. More about those arrows. This is how I actually coded each of them. The values for the on-axis arrows are showed here, and this is consistent with the magnetic field on axis and this equation when r is much greater than s. This is how I coded the perpendicular axis arrows, and their values are consistent with the equation for the magnetic field on the perpendicular axis. As you can see, the on-axis are double the perpendicular axis, which is consistent with these two equations. Next, we have the 45-degree angle arrow and the magnetic field at the 45-degree angle. This is the perpendicular distance, and this is how the arrow was created. It's all based off of this equation, which is consistent with the values that are printed out. And we have the conclusion. The magnetic moment of a bar magnet can be calculated by taking the absolute value of the magnetic field in the x direction at different distances using the Biot-Savart law. It was calculated to be 6.6134. The magnetic field of an off-axis bar magnet can be calculated by measuring the perpendicular distance and the magnetic field in the x, y, and z directions. The magnetic field is calculated to be 8.228 times 10 to the negative fifth teslas. VPython was used to visualize the magnetic field of a bar magnet as well as calculate the off-axis magnetic field, which is 5.71757 times 10 to the negative fifth teslas. These two values are different. There is some experimental error when I was calculating this. I did this experiment indoors. I was not able to do it outside, so there could have been some magnetic fields that were affecting this value. The value calculated in VPython is more accurate. If magnetic north was not compensated for, the distance that the bar magnet would have to be held at for R20, R70, R120, R170, and R220 would be off. If the x direction was greater than 0, the distance to read those values would be much larger than if the x direction read 0. And if it was less than 0, the distance would be closer to actually read those values. If two identical magnets were stuck end to end, the measurements would be different, because calculating the magnetic field takes into account the magnetic moment, which is calculated based on area, and would increase with an increasing length of magnets. Thanks for watching.